Welcome, everyone. It is a pleasure to have you here at the last seminar of the Asteroid Grand Challenge seminar series that we are running from SERVI, the Solar System Exploration Research Virtual Institute for NASA. My name is Yvonne Pendleton, and I'm the director here at SERVI, and it is my pleasure to welcome you to the seminar series. This is the last of our initial seminar series. We plan to have more in the future. This is an informative series to bring everybody into the conversation about near-Earth asteroids. And I'd like to give a special thank you to David Morrison, our senior scientist on the staff here at SERVI, who has been running this series for the past several months. All of the talks are archived on our website, servi.nasa.gov. And I encourage you to go back and check out any that you may have missed. If you have any problems or concerns during the seminar, if you have problems with audio or visual, please don't hesitate to type in a question in the chat box. We use Adobe Connect, and it's actually a very easy system to communicate with. And we can troubleshoot with you offline, or if it's a question that affects many people, it's good for us to know so that in that event we would stop the presentation momentarily while we solve the problem. Today it is my extreme pleasure to introduce to you our speaker, Dan Mazanek, who comes to us from Langley Research Center in Hampton, Virginia. Dan is a senior space systems engineer. He has 25 years of experience. His experience is in space mission and architecture formulation, conceptual design, and the sizing of human and robotic spacecraft. He graduated with a bachelor's degree in aerospace engineering from Virginia Tech in 1989. He was the Comet Asteroid Protection System Study Lead under NASA's Revolutionary Aerospace Systems Concepts Program in 2001 and 2. He also led the Langley Technical Analysis and Independent Technical Review of NASA's 2006 Near-Earth Object Survey and Deflection Study. He is a technical expert and a leader in the field of human and robotic missions to small planetary bodies. He has led multiple study efforts to investigate sending humans beyond low Earth orbit, including the development of a near-Earth object crewed mission concept study and the Mars Phobos Deimos preliminary destination mission concept study in 2012. He is the NEO mission lead analyst at Langley and serves as the near-Earth asteroid destination lead for NASA's Human Spaceflight Architecture team. He is currently leading analysis efforts for the agency's Asteroid Redirect mission. This is the option of robotically capturing a boulder from a large asteroid and returning it to cislunar space. He is a noted expert, and we are very happy to have him here today. Dan, thank you so much for giving us your talk today on NEA deflection strategies. It's all yours.
Okay, thank you very much, Yvonne. Appreciate it. Thanks to everybody for attending here live and the folks that'll be looking at this recording later on. I know there's been a lot of wonderful, very informative talks on the variety of topics surrounding the Asteroid Grand Challenge. What I'm going to talk today a little bit about is some of the deflection strategies that we can contemplate for actually deflecting or potentially also disrupting a impacting comet or asteroid. So the title slide that you see right here is kind of the gist of the presentation, is that we need to get to these targets before they get to us. And this is an artistic impression of an impact off the east coast of the United States, and then also deep impacts mission impact on a comet. So what I'm going to do is it's going to be kind of a high level, more of a high level talk, not a lot of numbers and equations, but there's certainly a lot of physics that's involved in this whole process. But let me start by talking about some of the basics of NEA deflection. First of all, as some of the other speakers have talked about, this is a natural hazard that can be prevented or mitigated given sufficient warning time and systems and technologies. So from a natural disaster standpoint, we don't know how to prevent an earthquake or a hurricane at this point. This is the one natural disaster that we can do something about it if we know about it. And basically it involves changing the impacting object's orbit so that it intersects the Earth's orbit either earlier or later than it normally would when unperturbed. So again, basically it's the analogy of the car coming across the train tracks. If you don't want to get hit by the train, or if you want the car to not hit the train, you make sure that you slow down or you speed up a little bit. Just make sure that the asteroid the comet is not in the wrong place at the wrong time. And usually you do this by applying a velocity change, call it delta V, in the proper direction. And this is typically along or against the impactor's direction of motion. And then you can see in this very simple diagram, an undeflected NEO impacts the Earth here, and then if you change that, it either arrives late or early. And again, about 6 minutes is required to have it arrive such that it misses the Earth's diameter, and the Earth's diameter travels that far during that period of time. So one of the key aspects is early response requires less delta V. And I know some of the other talks have talked about this. The mantra of find them early, find them early, find them early is very important. We also have to find them and also precisely determine their orbit so we can know whether or not they are an impact threat. And again, the idea is when we apply the delta V, we want to decrease the risk of impact from some number, whatever that original orbit uncertainty is, because space is a big place and there's always uncertainty in the orbit prediction. But we want to apply a delta V prior to impact so that we reduce the total risk to some acceptable value. And in the 2006 study, it was 1 in a million. You can pick your favorite number, you can pick your favorite Earth radius of what we think is safe, but that's the basic idea. So very quickly, near-Earth asteroids versus NEAs, what's the difference? Near-Earth objects include both asteroids and comets that have been gravitationally nudged to come near the Earth and possibly collide with it. So one way of defining the threat is to break it down into the types of orbits that they have. Either well-defined orbits, and this is the premise of the NEO detection and tracking system, so that we can provide warning time on the order of decades. There is uncertain orbits, so newly discovered near-Earth asteroids, maybe some short-period comets, where the warning time may be on the order of years once we determine that there was an actual impact threat. And then there's immediate threats. There's a class of comets, one of which is coming through our solar system later this year in October. They're called long-period comets. Basically, they have orbital periods of greater than 200 years. They may only have warning times of months. And in the case of 2013 A1 Siding Spring, which is going to have a very close approach to Mars in October of this year, we found that it was January 3rd of 2013. So less than 2 years for that, but there could be considerably less. And there's also the class of objects that we have no warning time for. Either they're unknown near-Earth asteroids, short-period comets, or long-period comets. And there we may have warning times on the order of days, or we may not have any warning time at all. So here's an example of a delta V application, and what this shows is there's 4 curves up here. It shows some different, a couple different asteroids, a short-period comet and a long-period comet. And the delta V that you need to apply is on the y-axis, and this is a logarithmic scale, so you got to be careful because every it's up by a factor of 10 for every line that you see, every major line. And this shows the time that the delta V is applied before the impact occurs. And this is simply the delta V to deflect the example impactor by 1 Earth radius. So just assume it's a dead center and you knew it perfectly that it was going to hit the center, how much would you have to apply just to get it to miss the Earth? And again, it goes back to how much you would want to move it, multiple Earth radii, for example, to be safe. But the main thing to get out of here is that if you have warning times on the order of about 10 years, the typical delta Vs are about a centimeter per second to a few centimeters per second. As that time goes down and you start to go down below a few years, you start to get up to 10 centimeters per second. And then if you're inside of a year, you're talking about meters per second of delta V that need to be applied. So again, finding them early minimizes that energy that needs to be, that momentum exchange that needs to be applied to the asteroid or the near-Earth object. So again, this is another chart. Now, I apologize because the x-axis flips here, but now to your left is 0 days to impact, and again, the delta V required. And you can see, this is just an example NEA, but if you want to just miss by 1 Earth radius, you know, and we're talking, let's say we're talking 10 years out, you're talking about like 1 centimeter per second, and this is a linear scale here. In order to reduce it by, say, 1 in 1,000, it's not that much different, but if you wanted to reduce it by 1 in a million, you may need several centimeters per second, and of course that goes up as you get closer. So, and this is a little bit of background, but it's all very important when you start understanding the different deflection techniques that we're talking about. And one of the key areas is impact uncertainty. Once you know where the orbit's going, you have to actually precisely know where it's going to hit the Earth, or you would like to. But that, again, is an uncertainty based on that time of arrival of the impacting object. So the exact impact point is going to be unknown. And on this this globe here, the red line represents the line of potential impact sites as an example. So, for example, you might have something, an impactor that might hit in Russia, which we've had a couple, or the Indian Ocean, or somewhere in between. This is what we call the risk corridor. And it is also altered during a deflection effort. So, for example, we're going to talk about some fast-acting and some slow-acting techniques, but if you apply a slow push-pull technique, that risk corridor moves, and it moves across the Earth's surface. So that has significant geopolitical considerations as you go forward with these deflection techniques. So, last thing, and I know this has been talked about in a couple of the other talks, but it's good to emphasize it again, is that NEAs have a wide range of orbits and physical characteristics. There's 2 aspects of characterization that are very important. First is to define whether or not the object is a threat. Precisely determine its orbit and doing a risk analysis using the available data to predict a probability of impact. You obviously don't want to go moving objects that aren't a threat if your goal is to defend the planet, unless you're practicing, for example. And so what you have to also do is characterize the object itself, the physical characteristics. Can be important for the deflection, disruption, or the mitigation technique. The size, the mass, the gravity field, the composition, the structure of the asteroid, and also the spin state and rotation rate are important, as well as surface properties like the regolith, any dust or surface charging. And of course, many asteroids, about 1/6 of the ones we know, have companions. So there is the possibility that there's 2 objects, and you have to deal with that. And again, the objects range in composition from very low density carbonaceous objects to stony to mostly metallic. They have vastly different porosity, so the amount of space that's in between the solid matter, as well as their structural integrity. So characterizing this both is critical to deflecting an impacting object. And one of the key tools that we have, and shown in the pictures here, are some of our radar observatories, absolutely key for determining the precise orbit of the object to determine whether it's a threat, and certainly some remote sensing information that can give lots of physical characteristics. Also, robotic precursors are extremely valuable to, be up close and personal to the object so that you can get some definitive characteristics that can be important. Now, that becomes problematic depending on the warning time that you have. So one last aspect before I get into some of the key aspects or key different technologies and approaches is a primary deflection versus a keyhole deflection. And Paul Chodas talked about this with respect to Apophis, that there's, I kind of talked about so far primary deflection. We're just trying to make it miss the Earth. But there is a set of locations in space called gravitational keyholes that are these small regions where an object can pass and then return on a subsequent encounter and contact the Earth. Now these probably only applies to a small percentage of impactors, likely less than 10%, but Apophis 2004 MN4 offered us an example of a keyhole potential impact. We found that it's not an impactor based on additional observations during 2013, but avoiding a keyhole requires much less delta V than does a primary deflection. And on this next slide, it talks about some different delta V's that are required. And again, these are to the right is the days before it actually reaches the keyhole, and this is for the 2029 keyhole encounter. And you can see, basically that design point 1 at the top, if you had about 10 years of warning time, you need something on the order of approaching a centimeter per second, about a half a centimeter per second. But if you were able to avoid the keyhole with some refined orbit knowledge that we would get between now and that encounter, you could reduce that by a couple orders of magnitude down to a fraction of a millimeter per second. It's very important to understand that and be able to take advantage of that. So with that kind of introduction or background, I'm going to go through some of the different techniques for deflecting an asteroid, and could be applied to a comet as well. And they're basically broken down into two classes. The first is what we call rapid impulsive techniques, which, everything provides an impulse, a momentum transfer, but these are fast-acting approaches. They produce immediate results. The effectiveness is dependent on the NEA properties, which have some high uncertainty and variability. They typically produce large concentrated forces that have the potential for fragmentation or disruption. And some examples, the typical ones are kinetic impactors, where we take a high-speed projectile, spacecraft, or other material, and basically slam it into the object. And this was demonstrated by the Deep Impact mission on a comet. There's also the use of conventional explosives, either surface or subsurface. Of course, these approaches don't have the energy content that's very efficient, so there's aspects there of how effective it is. And of course, you have the nuclear detonation approach, either a standoff, a surface, or a subsurface approach, with the potential for the delivery system to actually use a very high velocity impactor, similar to the kinetic impactor. You also have slow push-pull techniques that are long duration, acting over many months to potentially years, depending on the size of the asteroid. And they apply a very small force on the asteroid, but do it for a long period of time. So you have a low acceleration, but using time as your ally, you can create quite an increase in the delta V. Typically, these approaches have efficient use of resources that are typical in spacecraft, the propellant, the power available, as well as in situ materials. In the fast-acting, the impulsive techniques, and we'll talk about this more, is the nuclear detonations probably are the most efficient mass use that you have out there in terms of the ability to translate mass into energy. But for the slow push-pull techniques, there's basically four categories. Either you can try to enhance the natural effects of the asteroid or comet, or apply a contact force where you physically touch the surface. You can apply physically touch the surface with the spacecraft or with some other means, and I'll talk about the differences there. Apply a gravitational force where you utilize the laws of gravity to affect the asteroid, which of course is how the asteroid's there in the first place. We're all bound by the gravitational force of the sun. And then also use ablation or expulsion of the surface material. And some of these examples are what we call an albedo thermal response modification, or sometimes known as painting the asteroid. This takes advantage of the Yarkovsky effect, which is a thermal re-emission of energy. This technique, I mentioned here, I don't have a particular slide on it, but it's likely to take centuries of effect in order to affect, say, a 200-meter type near-Earth asteroid. Smaller ones may be a little bit more effective, but it's a natural effect that actually moves asteroids within our solar system, and it's partially responsible for the reason in the first place why there would be an impactor. There's the direct push, which I mentioned, and we kind of call this the space tug. You can think of it as a barge pushing a tanker. There's mass drivers, where you actually take material off the surface and throw it at high velocity from the asteroid, thereby creating a momentum transfer. There's the gravity tractor and the enhanced gravity tractor, and I'll explain the difference between those in a couple slides. There's the ion beam deflection, which utilizes the particles coming out of a solar electric propulsion vehicle to actually impinge on the surface and utilize that in essence a series of mini kinetic impacts on the surface to change the velocity. And then you've got the surface ablation approach, where you can either use a high-powered laser or a solar concentrator to affect it. So out of the 2010 National Research Council Committee, one of the primary findings was that no single approach to mitigation is appropriate and adequate for completely preventing the effects of the full range of potential impactors. Civil defense is an appropriate component of mitigation in all cases. Certainly, we want to take that into account and understand the aspects of civil defense: warning, taking shelter, evacuation. With adequate warning time, though, a suite of 4 types of mitigation is adequate to mitigate the threat from nearly all near-Earth objects, except the most energetic ones, like the potentially the long-period comets and the very, very large asteroids. And you can see the strategies there range from civil defense, the slow push, for example, a gravity tractor with a rendezvous spacecraft, kinetic impactor, and nuclear detonation. And again, the slow push, you have to have warning time, and its applicability as you get larger and larger gets reduced. And potentially for large threats and short warning time of medium-sized threats, that a nuclear detonation may be the only option that we have. So again, find them early is a good mantra. So going through just some notes about kinetic impactor. This is a very high-speed, high-velocity impact collision with the asteroid, typically greater than 5 kilometers per second. And of course, the kinetic energy is based on 1/2 mv squared, so 1/2 times the mass times the velocity squared. So as you can get up that velocity higher and higher, the effect of that is much greater on the energy that's imparted from that kinetic impact to the asteroid. It's a relatively simple technique. We've demonstrated it on a large cometary body, or a larger cometary body with a reasonable mass. In 2006, we had about a 370 kilogram impactor at 10 kilometers per second. And it's likely the method of choice for less than 500 meter impactors, provided that we have sufficient warning time. And the effectiveness is dependent on the structure of the asteroid. If it's solid, the effect of that kinetic impact is going to be much different than if it's a rubble pile and it has high porosity. And this, there's this we call a beta factor, which is a momentum exchange efficiency. And there's a lot of uncertainty. There's a lot of ground testing that's been going on, but certainly testing these concepts on real targets in a real environment is important to understand the range of efficiencies that you might have. Additionally, terminal targeting becomes more difficult as the relative velocity increases. So if you want to get the velocity up higher and higher, that last period of time where you have to make sure that you hit the target and do course corrections becomes more critical. So for nuclear detonation, it's probably, again, like I mentioned, one of the most mass-efficient deflection techniques. And again, you can either do a standoff where you detonate the nuclear device at some distance from the surface and basically allow the energy to ablate the surface and provide the momentum exchange. Or you can place it on the surface or put it down in the subsurface so that you get a large throw-off of material, which results in that momentum exchange. And currently, it's probably the only viable option for large asteroids, something that's greater than, say, 500 meters in diameter, with relatively short warning times on the order of months to years. And again, as with the kinetic impactor, the structure is a key aspect of the nuclear detonation option. A dissipative low-density surface results in less ejecta and therefore lower delta V imparted. And you can see in the bottom right is a hypervelocity asteroid impact vehicle concept that's been proposed at the Asteroid Deflection Research Center at Iowa State. And what you can do with that is basically use the kinetic impact approach to deliver a subsurface detonation. And we can test out these types of techniques with or without a nuclear explosive on there. So you can test the kinetic impactor and see if this is possible, because there's still a lot that we need to learn about these different types of techniques. So this is quite a busy chart, and this is from the 2006 Near-Earth Object Survey and Deflection Study, which was, the summary was given out to Congress in 2007. And I'm not going to go through all this, but it's basically the message that you want to get out of here is this is, on the y-axis is the effective momentum change, and it's measured here in kilograms times meters per second. And as a function of the deflection vehicle launch mass. Now there's a lot of assumptions that go into this chart that was produced, but the trends are pretty consistent with varying assumptions. You can see that the amount of launch vehicle, how much mass you would have to send to the asteroid in order to provide some momentum exchange. And if I bring up the pointer here, the way to kind of read this is if you wanted to apply a 1 centimeter per second on, say, a 200-meter object, so something about 10 to the 10 kilograms, kind of come over here, and then anything that's above that can provide that momentum exchange at a particular launch mass would be viable. So you can see that first of all, that you require larger launch mass depending on how much energy you have to provide. And then some of these techniques, the conventional subsurface in particular, and some of the kinetic impact techniques with a lower beta are not very effective at providing that momentum exchange for those larger type of objects and that high delta V. And going into some of the slow push-pull techniques are shown here. This approach is the first one is a direct contact, and classifying that as the space tug and the mass driver. So with these approaches, and I'll turn off my arrow now that it's on the next page, sorry about that. This approach requires some extended mechanical connection with the asteroid. It can utilize the high specific impulse, say of a solar or nuclear electric propulsion system. If you try to use chemical propulsion systems, you're probably in a situation where your mass, you can't send enough mass there, enough propellant to effectively change the orbit. And of course, the rotation of the near-Earth asteroid, which could be on the order of hours or days, but could be as fast as minutes. The rotation could be drastically different, and it affects how effective this technique is. Because, as we mentioned before, you typically, with a sufficient warning time, you want to push the asteroid along the path or against its path of motion. And if this object is rotating, potentially tumbling, you have a very limited time when you can properly apply that propulsive technique. Mass drivers add the complexity that you have to harvest the material and eject the material from the surface. And although these are viable techniques and they could be utilized particularly on smaller objects, our current lack of understanding of small body surface and subsurface characteristics, they increase the risk of these approaches. And the next slide, if it comes up, let me try this one, okay, is the gravity tractor. And I call this standard and enhanced, but basically both techniques use the mutual gravitation between the asteroid and the spacecraft to change its orbit while the spacecraft maintains a separation distance. Now again, this is facilitated by a high efficiency propulsion system like solar electric propulsion. where we have what we call the specific impulse, which is kind of like the miles per gallon that you get out of your car, the efficiency of the fuel system. The best chemical ISPs are on the order of 450 seconds, and that's how the units are measured. Electric propulsion may be several thousand seconds of ISP. So you have, we're looking at systems right now that are 2,000 to 3,000, and certainly in the future we might have 5,000 to 10,000 second ISP. So for every kilogram or pound of propellant that you bring, you get a lot more force that's generated. Now the gravity tractor, if you're only using the spacecraft, and you can see in these depictions, these pictures, you maintain a standoff distance, and you can either do that in front of the asteroid, or you can use a halo orbit concept. And there's pros and cons of those different techniques. The halo, because you're trying to maintain that separation distance, you don't want to plume on the asteroid, because that negates this very, very weak minuscule gravitational effect that you use over time. So with the halo orbit, you can point your thrusters and not impinge on the surface. But in any case, with just the spacecraft, let's say you have a 5-ton or maybe a 10-ton spacecraft, it requires a significant extended operation on the order of years, maybe longer than 10 years, therefore requiring long morning times. The enhanced gravity tractor approach uses a mass augmentation at the near-Earth asteroid. So similar to the mass driver, you obtain mass from the surface, but you don't have to stay on the surface. So you do have to contact the surface to collect a sufficient amount of material, whether that's a single boulder or piece of material or regolith captured. But once you collect that material, now you can enhance the effect of this gravity tractor deflection potentially by a factor of 10 or more, which has a commensurate effect on the amount of time that you need to spend there. So for smaller objects and for doing keyhole maneuvers, the gravity tractor may be a very effective way of mitigating or changing the orbit of that asteroid. As I mentioned, the halo orbit increases the operational efficiency, so it keeps the plume away from the asteroid. In addition to that, it eliminates thrust losses, and because you're not canting the thrusters, you have additional control authority. So if you're out in front, you have to cant the thrusters, so you have some cosine losses. And in the case of the halo orbit, you don't have to do that. And finally, what it allows you to do is have multiple spacecraft working cooperatively. So you could have 2 or 3, maybe more gravity tractors, all spaced in this halo orbit, working like a team of horses to pull a sleigh. The ion beam deflection technique would utilize that same sort of electric propulsion system, but here, in this case, you actually want to point the thrusters at the asteroid and use those particles, those high-speed plasma particles, to create a force and or a torque on the target. So you potentially could use this technique to alter the spin state, which could be effective if you want to do a kind of a hybrid approach of landing on the surface as well, to kind of set up the asteroid rotation rate to the optimal in an optimal manner. It uses a second set of thrusters along with the propellant to counter the thrust, so that you maintain your position. Because if you start thrusting and you're just going to move away from the asteroid, and if you stop thrusting, you're either going to stay or be pulled back slightly based on the gravity. So if you have a single set of thrusters, you have to go back and forth. If you have a dual set of thrusters, you can maintain position, but you have to use the propellant in order to do that. So again, you can have continuous thrusting without physical attachment to the asteroid, which is beneficial. And the efficiency really depends on the beam divergence. So if you have a very tight culminated beam, you can get high efficiency here. But if there's a large plume angle that comes out, the divergence angle, then that minimizes the effect. Finally, there's surface ablation techniques. And again, the pictures that show here show a rendezvous, both show rendezvous spacecraft, one showing a high-powered laser system, one showing a solar collector using the sun's energy. Again, the nice thing about these techniques is there's no surface interaction required. You have to generate a high enough temperature to ablate the surface, to basically melt the surface and sublimate it and turn it into a quasi-gas state. And only station-keeping propellant is needed for the spacecraft, so there's not a lot of propellant that's needed. It's effective on a wide range of surface materials. It's insensitive to the rotation rate, to first order. So as the object rotates, you just focus the beam on a particular point, and you get a blow-off of material in a controlled, low acceleration manner. And of course, this is non-disruptive. So, for example, if you have a binary system, if you do a fast-acting technique, you have the potential to disturb the system. And the question is, what will that binary do? If you apply a low gravity, a low acceleration technique, then you have a much higher chance of keeping a binary system intact and pushing it. Now, the downside here for the laser systems is, as you get larger, you need more energy, which requires multi-megawatt to potentially gigawatt class electrical power systems, along with the thermal management, et cetera, that's required to manage that thermal energy. The solar ablation also requires large concentrator mirrors or lenses, and the secondary mirrors must accommodate very high heating loads as you concentrate this energy. And finally, sufficiently accurate spacecraft pointing is needed to maintain that spot on the surface of the asteroid for an extended period of time. So again, you can see here that's a similar chart to the one I showed before. As a function of the effective momentum change and the launch mass, you can see that these slow push techniques, and these are again some concepts that were used with certain assumptions, are much less effective at applying that effective momentum change as a function of the vehicle mass. So again, as we can get solar electric propulsion more efficient, those masses will shift. Just a quick comparison in a kind of a red, yellow, green, blue readiness format here. Both the readiness and the effectiveness of impulsive concepts and slow push concepts. And you can see the slow push concepts, we have a much lower readiness because we haven't demonstrated them. We have a lot of technology development that applies. And their effectiveness is classified as low to medium. The impulsive techniques have much higher readiness, and the effectiveness varies from medium to potentially very high. Now, again, these are just a comparison, and these are very kind of subjective. There's a lot of variation between these colors. The other thing is the characterization required for impulsive approaches. And first of all, the mass is something that's required. You need to know that. For most of them, you don't need to know the spin state necessarily, because you're impacting so quickly. You just have to hit a location on the surface. The surface delay type of a nuclear explosive would obviously need to know and time it correctly so that the spin is important. Other material properties, density, the structure, the size and the shape, and the surface properties are helpful or not needed. So there's a lot of, it's insensitive to the type of target. To first order, there are some secondary effects and considerations that are important. The slow push-pull approaches are much more dependent on the properties and understanding the characteristics of the object. And then finally, the issue is, again, reaching the target in time. Getting to the impactor before it gets to us is the goal. And we talked about the detection, tracking, and characterization of the critical first steps, but they only would provide a civil defense mitigation if we can't do anything to stop the impact. So the critical capability is to be able to deliver the deflection payload to the impacting object. That means we need to have sufficiently capable launch vehicles. Heavy lift launch vehicles are very valuable as long as they're reliable. So not only is the mass of the launch vehicle important, but the reliability obviously is critical as well. We have to have efficient and reliable in-space systems, propulsion, guidance, control, etc. If we launch it effectively and the spacecraft fails en route, then you have to have a contingency backup, or you have to send multiple spacecraft, which we may want to do anyway to guarantee the deflection. And the systems must be capable of delivering the required mass in sufficient time. So again, low thrust is very efficient at throwing mass out quickly, but it can't throw as much. High thrust takes more time. So It's just interesting to kind of think and reflect back that telescopes and rockets may end up being the two most important inventions in human history, to be able to find these objects and be able to get to them before they get to us. And again, the NRC 2010 NRC committee recommendation was that if Congress chooses to fund a mitigation research at appropriate high level, the first priority should be a kinetic impactor, and it provides the most significant advances in understanding and provides an ideal chance for international collaboration in a realistic mitigation scenario. So that was the recommendation there. Couple last slides on developing these systems. This is really the crux of the matter, is how much do you spend, when do you develop a system, do you wait for technologies? And the technologies I've shown here are pretty much existing or in the near future. There are certainly more exotic technologies that can be contemplated and have been contemplated in science fiction and maybe even science fact at this point, but they're not ready for deployment. So, you might have up to a decade of development schedule for these. The kinetic impactor is probably the shortest. And if we don't have sufficient warning time, it may not be enough. So basically, you need to have a toolbox. One approach doesn't work for every situation. You can use multiple approaches, can provide a comprehensive approach, and multiple spacecraft and technique can be employed. So for example, you can use a kinetic impactor for primary deflection, and then a low thrust push-pull technique, a slow push-pull technique to clean up or provide trim maneuvers. And demonstrating and evaluating multiple approaches is needed to increase our understanding of the effectiveness, both on the same target and as many different targets as possible. And of course, there's a key aspect of latency time, and I define this time as the time between the decision to act and the initiation of the deflection effort. And that can be reduced dramatically by demonstrating techniques well before discovering an impactor. So this just has, and I've kind of covered most of these, this has some examples of how these technologies are synergistic with both planetary defense and space exploration, both human and robotic. And we've kind of talked about all these techniques, including the rendezvous and station keeping. And just as one other aspect of the synergy is the compatibility between resource utilization and planetary defense. These asteroids and comets, they represent both a valuable resource for space development as well as an inevitable threat. It's simply a matter of not a matter of when, of if, but when. And right now, we don't have any dedicated planetary defense system. Are we going to be able to fund something like that? But that due to the infrequency of the impacts, that might be unlikely. So developing these technology systems, and particularly the operational approach, is important. Again, the different techniques can be employed. And I really think an integrated solution is something that needs to be considered. If we start learning how to efficiently move large amounts of useful material around the solar system to provide benefits, for example, economic potential of near-Earth asteroids or for space travel, you start to generate the foundation of an on-call planetary defense system. And so you don't have the development, you don't have the launch risk and the time, and you also have the personnel that are trained and proficient in operating the systems. So we can solve what I call the impact dilemma, and that is, how do you fund a planetary defense system in time when you can't afford to fund it? And the analogy I like to close with is using bulldozers for snowplows. You can't take petition a municipality and convince them to buy a fleet of snowplows if they never experience or very seldom experience a snowstorm. But if you have bulldozers, if you have a fleet of bulldozers that are doing construction and providing economic value, they can be used in a pinch as a mitigation technique. They may not be optimal, but they certainly can be an effective approach. So with that, I'll close, and I thank you for your time and attention. And if there are any questions, I'll be glad to take them now.
Great. Thank you so much, Dan. Okay, we have some wonderful questions that have come in while you've been speaking, and I'm just going to start reading down the list. We will start with the first one here I see is from John Allen. When you apply delta V, can you anticipate the downstream effect, where it goes next? Will we be creating a problem that comes back to haunt us later by possible collision with another body?
Yeah, so certainly the proper application of that delta V is an important aspect. We have the ability to apply these techniques sufficiently accurately, and we have the ability, particularly if you have a spacecraft that is in close proximity, to measure the effect of that change. And of course you would do so in a manner that makes the situation worse rather than, makes the situation better rather than worse. You don't want to make it worse. So that's why, in particular, we need to practice, because eventually we are going to be faced with a situation where we have to do it. And the better that we understand how to apply these techniques, and if we can have sufficient warning time, we can apply the technique, predict the orbit well into the future, and then make sure that the threat has been properly mitigated. So I think we absolutely have the technology to apply it properly, and we have the understanding of the properties of and the changes in the orbit, and being able to propagate those orbits out many, many years into the future, for asteroids potentially hundreds of years into the future.
Okay, great. Another question, are 1 in 100 odds enough to justify asteroid redirect?
Yeah, so that is an interesting question, and that gets into the politics and the probability of impact, what type of object it is, how large it is. If it's a very, very small object and it's 1 in 100, it might not make sense to launch a mission. If it's a very large object, again, it's a matter of time. As time goes by, if it was an impactor, at some point it would be 1 in 100, and then it would increase until you have certainty. Typically, and thankfully, most objects are not going to hit the Earth. So what we have is a situation where there's a probability of impact, and the probability of impact potentially goes up a little bit, and then it goes down because it's not an impactor, and as we understand the orbit better. But it's that aspect of when do you act, and that affects that latency time that I talked about. When do you convince governments, depending on the nature of the threat, that it is a threat, it's confirmed. So that's where the orbit characterization, the precision orbit determination, is very important, as well as the remote characterization. And finding them as early as possible allows us to potentially send robotic precursors out to them, or get additional radar observations that either eliminate that threat or increase that probability that it is going to be an impactor to a level that people respond to. But bottom line is, there's a lot of discussion about at what point do you make a planetary defense effort, and it's still an open question.
Yes. Okay, so can a near miss cause damage brushing the upper atmosphere? And I think related to that is the next question, will nukes disrupt the local plasma media? Okay, so
typically, we have objects that graze the atmosphere, and some of them skip and bounce out. We've had some meteor shows that or bolides that have done that. Again, it depends on how large the object is. Our atmosphere is very thin, but if the object's large enough, obviously if it gouges in the atmosphere, it could have some effect. But for the most part, the typical size objects that we're seeing probably would not have an effect there. And the second part of the question with respect to the nuclear, if I understand that correctly, are they asking about the Earth's magnetic field, plasma field?
It just says the local plasma media.
Okay. So if we're talking about the nuclear deflection technique on an asteroid, if you do, for example, a standoff nuclear blast, yeah, there's a lot of complex physics that are involved, but some of our nuclear scientists have characterized those quite well based on our various defense analyses that we have, capabilities, dynamic flow codes. The effect of that is also dependent on the surface material, but energetically there's probably not a significant effect of the plasma field in that type of an explosion. It happens so quickly, and there's a certain amount of mass that's expelled that they pretty much characterize that pretty well.
Okay,
I'm understanding the question.
And I think you've said something about this next one, but maybe you'd like to say a bit more. Which methods are the most cost effective, or what it says, don't want to distract from the great science, but which methods are most cost effective?
Well, so that's kind of a question. Certainly there are the spacecraft development, the operation, the launch vehicle costs, and when you say which is effective against a smaller or a larger object. So let's take a larger object. Let's say something that's 200 or 300 meters in diameter, for example. So something that would cause regional to significant catastrophic effects on the Earth. And of course, if it lands in the ocean, it could have global effects through the tsunami. So if you launch multiple impactors, that's one way of doing it. If you launch a single nuclear device, the development costs for that nuclear device have to be factored in. So it's kind of hard to necessarily pin it down exactly. The other aspect is with the asteroid redirect mission that we're talking about doing the enhanced gravity tractor approach for one of the options, the robotic boulder capture option that we've been looking at, and then bringing that boulder back to cislunar space. That spacecraft itself, if there's enough fuel, or if the spacecraft could be refueled, after missions to investigate the asteroid or the boulder, for either option that we're looking at, you could actually use that same SEP system and the remaining material as a kinetic impactor. So it kind of goes back to this idea of bulldozers for snowplows, is that if we have systems capable for space exploration, for mining resources, we can then use them when needed. And to me, that's the most effective, cost-effective approach, is that you get that dual use out of the systems, and therefore, to first order, the planetary defense technique is free, and you take advantage of the resources that you have.
Okay. Let's see. It says, this may be on the fringe of the topic, but are there any thoughts to limiting public knowledge of unnecessary hysteria-causing speculation when an actual threat arrives?
So Lindley Johnson would probably be the best person to answer that question, but that I really can't comment. I think the way that our system is set up, it's a very open public exchange of astronomical information. And that's one of these social issues that needs to be addressed, as to how much information, can it be a good thing or can it be a detrimental thing, especially with the uncertainty. So I can't speak for NASA. My personal opinion is that information is good and that we should share information to the greatest extent possible. I think that people make rational decisions when presented with good information. But that's a policy issue that's definitely above my pay scale.
Okay, well, Lindley has actually written in here. Thanks, Lindley. He says, NASA's policy on release of information to the public on a potential asteroid impact is to provide the best information available as soon as it is verified as credible to the public. That is the best way to avert the harm that may be caused by alarmist speculation. Agreed.
So, okay, yeah, I agree with that.
Okay, good.
Thanks, Lindley.
So we have another question. Do any of these techniques have potential dangerous side effects for us or for spacecraft?
And when it says for us, well, certainly the goal of deflecting an asteroid or a comet would be to change its orbit so it doesn't hit us. Any of the techniques, particularly the fast-acting techniques that disrupt that potentially fragment or disrupt, could have a negative effect. Is it better if there was an impacting object? Is it better to have a single object or multiple objects coming through the atmosphere if the object's disrupted? and certainly for those fast-acting techniques, you're not really worried about the spacecraft like a kinetic impactor. Typically, the spacecraft is the kinetic impactor, although you could come up with scenarios where you have a spacecraft that co-orbits or does a flyby as a separate impactor hits the surface, like we had with Deep Impact, to monitor and get the orbital deflection measured properly. So again, it goes back to warning time. And if we're presented with a situation where we have virtually no warning time, disruption or fragmentation may be the only technique that we can use. And we hope that situation never arises, because we want to be have a robust observation and characterization program. But in the end, we do have a force field around our planet called the atmosphere that is very very well adapted to disintegrating smaller asteroids. Typically 10 meters, we get hit on a yearly to decadal basis by 10-meter-ish objects, and they burn up harmlessly in the upper atmosphere. Now, the Chelyabinsk meteor in 2013 in February was an object that was about 19 meters in diameter. So again, it's a matter of if you do the techniques right, you do them early enough, we deflect the object, it stays far away from the Earth, so there would not be any effect on us.
Well, related to that is a good question that says, do we have work in progress for practice shot for the 2029 NEA approach?
Well, part of the asteroid redirect mission that we're looking at is going out to a different body, not Apophis, but demonstrating planetary defense techniques, and that would happen in the 2020s. So you could look at that as a practice shot, and we're still looking at the different techniques that we can demonstrate on that. We have the option of capturing an entire small asteroid or retrieving a boulder from a large asteroid, something of 100-meter plus size, and we can demonstrate a kinetic impact with that mission. Right now we're baselining the enhanced gravity tractor, but we can also do the ion beam deflection. So right now the 2029 Apophis approach will not result in a keyhole passage, and there's no threat of an impact from that object in 2036. So we don't need to do anything for that approach. But again, the sooner that we start practicing, the better.
Okay, and we have a question. Would certain methods be ill-advised for binaries?
Yeah, I addressed this just briefly during the talk. Again, the space is a big place, so even if you have a technique that disrupts a binary, the chance that that binary, if given sufficient time, is released from the parent asteroid is probably a very, very astronomically low probability that would become a threat. But it could be, depending on how that process is done. So again, getting them early and affecting the change and being able to do it in a controlled manner is important. So some of those slow push-pull techniques that I talked about, the accelerations on the parent body are so low that the companion would stay in orbit and would not be thrown out from the gravitational attraction of the parent body.
Okay. We have a few more questions, but given that we're at the top of the hour, I'm going to suggest that people take the questions offline and talk to you directly, Dan. I'm sure that you'd be happy to answer more questions. I'd like to, at this time, thank you and, in fact, all of the speakers that we've had in this seminar series. This was just another great example of the wonderful talks that have been given in this series. I really thank you quite a bit. I learned a lot. I'd also like to thank our technical staff here at CERVI, especially Ricky Guest and Ashkan Nijad and Maria Elias. I would like to thank David Morrison for organizing this seminar series. And if we have a follow-up, a second season of the series, it would probably start in the fall. So please watch our website at survey.nasa.gov to find out if that's going to happen. And we will also try to alert you through all the normal mechanisms that we have. I think that's it for Survey Central. We would like to thank NASA headquarters and Jason Kessler for the idea and for everything that everyone is doing on the Asteroid Grand Challenge. Obviously a very important topic. And Dan, thank you again for a very wonderful talk.
Thank you.
Bye-bye.
Appreciate it.